Yashasvi and today we are going to discuss a very interesting topic, that is hydrogen bonding. This topic is interesting because this hydrogen bonding is not as common as ionic or covalent bonding. What makes it so special is it's a bond that forms between two electronegative atom and hydrogen. We'll discuss this later. First of all, when did this idea arise? So in 1920, Latimer and Rodebush gave this idea to explain the nature of association of molecules or substances in liquid state. Those substances were water, ammonia, hydrogen fluoride, formic acid, and few other. So what happens here is, in hydrogen bonding, a hydrogen lies between two highly electronegative atoms and shows a very unique property of forming a bridge or linkage between these two atoms by forming a covalent bond with one, and while purely electrostatic force of attraction with the other. Let's take an example. And where the hydrogen bonding is seen. I am taking the example of HF, that is hydrogen fluoride. Since fluorine is highly electronegative atom, it forms a delta negative charge on it and delta positive on hydrogen. And this bond here forms is purely covalent. But due to this formation of delta positive and delta negative charge on the hydrogen and fluorine of two molecules, so the hydrogen of one molecule forms another weaker bond by the dipole-dipole interaction, which is called hydrogen bond. So here it states that, so it's simple that a hydrogen bond is formed when a hydrogen lies between two highly electronegative atoms with small radii and forms a covalent bond, and electrostatic force of attraction causes another formation of a bond which is weaker than the covalent bond, is called hydrogen bonding. So if we talk about the strength of hydrogen bonding, hydrogen bond is weaker than covalent and ionic, but it is stronger than van der Waals force of attraction. So its bond energy that is seen in van der Waals force of attraction is less than 8 kilojoule per mole. While in hydrogen bond it is seen of 8 to 42 kilojoule per mole, and in case of covalent and ionic it is 200 or more than 200 kilojoule per mole. So here if we see the covalent bond that is formed is with the energy of around 200 kilojoule per mole, and this weaker bond forms with energy of around 8 to 42 kilojoule per mole. So if the question arises, so according to this, if the question arises, this hydrogen bond is formed between A and B atom with A as X and B of Y energy, then bond energy of X would be, which of these is correct option? Bond energy of X is higher than bond energy of Y. Bond energy of X is equal to bond energy of Y. Bond energy of X is smaller than bond energy of Y, and B, none of these. So if this question arises, you should be 110% sure that this is the correct option. But there is an exception here too, where this will be also possible. It comes in case of HF2 negative. Here there is a presence of lone pair and hydrogen bonding because of presence of lone pair. Here, bond energy of covalent bond become equal to bond energy of hydrogen bond. This is an exception of HF2 negative. Otherwise, this first option will always be correct. Okay. Moving forward, with this much amount of information, we came to conclusion that if we want to form the conditions for forming of hydrogen bonding are first, the electronegative atom should have electronegativity of 3 or more than 3. And second, the size of electronegative atom should be small. And electronegativity is inversely proportional to size. So smaller the size, higher will be the electronegativity. This will lead us to the conclusion that fluorine, oxygen and nitrogen will form hydrogen bond with hydrogen because of their high electronegativity. Fluorine has the electronegativity of around 4, oxygen has 3.5 and nitrogen has 3. Now what comes into our mind, why are we not considering chlorine? So chlorine is not considered here because of its size. Chlorine is large in size and that is why it does not form hydrogen bonding. So as we see in HCl molecule, there is no hydrogen bonding in that. Okay. Moving forward, there are basically two types of hydrogen bonding. One is intramolecular hydrogen bonding and the second one is intermolecular hydrogen bonding. So as the name suggests, intramolecular hydrogen bonding basically happens when the hydrogen bonding is seen in a single molecule. Here chelation is seen, that is cyclization. While in intermolecular hydrogen bonding, two or more molecules that can be same or different forming hydrogen bond. So example of this is hydrogen chloride, water, ammonia, and if we see alcohol with water, etc. In this we can also see a property of dimerization seen in carboxylic acid and boric acid, etc. So let's begin with the examples of the first one, that is intermolecular hydrogen bonding. So yeah, first example that we are taking is of HF, that is hydrogen chloride. Hydrogen chloride, this one down. This is covalent bond, this is hydrogen bond. This is the first example. Hydrogen The second example comes of water, where intermolecular hydrogen bonding is seen. HOH. Third example that comes here is ammonia, NH3. So happens intermolecular bonding. Intermolecular hydrogen bonding is seen in ammonia. And the fourth that we talked about is alcohol with water. So alcohol is ROH and water is H2O. So if we see, ROH forms hydrogen bonding with HOH. These are the examples of intermolecular hydrogen bonding. Along with that, I have talked about the dimerization. So dimerization is seen in usually intermolecular, where intermolecular hydrogen bonding takes place. That is in carboxylic acid. Let's talk about carboxylic acid. So R, C, double bond O, O, hydrogen bonding. Hydrogen bonding with oxygen, oxygen. There is R. So here dimerization takes place due to presence of intermolecular hydrogen bonding. So if the questions arises that the molecular weight of molecular mass of actually carboxylic acid or maybe boric acid is double of its original. Why? Then you have the answer here. Because of dimerization, the two molecules dimerize, and because of intermolecular hydrogen bonding, and this causes increase in the molecular mass of carboxylic acid or boric acid. Moving toward intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Here hydrogen bonding takes place in single molecule. Its examples are ortho, nitro, phenol. Let's take example. This is the example of orthonitrophenol, which is first example of this, and second example of this is ortho hydrobenzaldehyde. This is also called salicylaldehyde or salicylic acid. Because of the presence of what's the importance of hydrogen bonding is presence of hydrogen bonding, it causes high boiling point and melting point, first thing. Second, dimerization of molecule. That is association. Third is required more energy to break. Therefore, it causes high boiling point and melting point. And cyclization slash oxidation in intramolecular hydrogen bonding shows low boiling point and melting point because there is no OH release. There is no chance of releasing of OH. No. Solubility decreases. Intermolecular hydrogen bonding solubility increases.